A stone temple can stand for 1,000 years without steel or concrete. The ancient engineering secrets behind these structures are a mystery we are finally solving. By the end of this video, you will understand the precise, forgotten principles that allowed temples to survive earthquakes, monsoons, and the relentless passage of time. We will uncover how builders created foundations that dance with tremors and stones that fit together without a trace of mortar. What timeless wisdom did these ancient masters possess that our modern world has overlooked? This drive for permanence was the very bedrock of their philosophy. Think about the difference between building a house and building a universe in stone. For these ancient architects and the communities they served, a temple was far more than a place of gathering. It was a sacred anchor point, a physical manifestation of divine order and cosmic harmony. Its purpose was to bridge the world of humanity with the realms of the eternal, and such a bridge could not be temporary or frail. This wasn't about creating a shelter that would last a lifetime. It was about forging a monument that would withstand the turning of ages, a testament to faith and craftsmanship intended to outlive empires, languages, and even the memory of its own creators. This cosmic perspective is the first and most crucial secret we must unlock. It explains why they would reject a quicker, cheaper method in favor of a technique that took generations to complete. Every decision, from the quarry where they cut the first stone to the final placement of the capstone, was filtered through this single question: will this ensure our work endures for 1,000 years? This long-term vision eliminated shortcuts. It demanded materials of incredible strength and stability, stones that would not weather or crumble. It required a site chosen not just for convenience, but for its geological solidity, its alignment with celestial bodies, and its sacred significance. Most importantly, it fostered an unparalleled culture of precision. When you are building for gods and for a future you will never see, you do not settle for good enough. Every surface had to be true, every joint exact, because the integrity of the entire structure, and by extension the cosmic order it represented, depended on it. This mindset transforms the temple from a simple building into a conversation with eternity. And to hear that conversation, we must listen to the stones themselves, starting with the very ground they chose to build upon. The ground beneath a temple is its first line of defense. In regions where the earth itself is restless, where the ground can shudder without warning, ancient builders faced a paradox. They needed to erect monuments of immense, unmoving weight, yet the foundation they stood upon could not be rigid. Their brilliant solution was not to fight the earthquake, but to invite it to dance. This is the art of seismic isolation, a secret mastered millennia ago. Instead of anchoring their temples directly to bedrock with unyielding bonds, these engineers often created a deliberate buffer zone. They would excavate deep pits and fill them with alternating layers of sand, rounded gravel, or even crushed stone. On top of this, they would lay the enormous stone platform that served as the temple's base. Think of it not as a solid anchor, but as a massive stone raft floating on a bed of ball bearings. When seismic waves roll through the earth, this flexible foundation does something extraordinary. It absorbs the energy. The layers of loose material shift and move, allowing the heavy platform above to slide and rock ever so slightly. The violent, jerking force of the quake is transformed into a gentle, swaying motion. The temple above experiences a slow, rhythmic rocking instead of a sudden, catastrophic snap. This principle is visible in the colossal stones of the Temple of Jupiter at Baalbek, resting on layers of fill that have allowed it to withstand countless tremors along the Dead Sea fault line. We see it in the precise, interlocking foundations of Machu Picchu, where terraces and temples move independently during quakes, preventing a chain reaction of collapse. This was not magic, but an intuitive, profound understanding of dynamic forces. These builders understood that sometimes the greatest strength lies in controlled movement. They designed their temples not as rigid monoliths, but as resilient entities that could sway in harmony with the Earth's vibrations. This ancient insight into damping energy, of isolating a structure from the worst shocks of the ground, is a cornerstone of modern earthquake engineering. Yet it was practiced with stone and sand over 2,000 years ago. It reveals a mindset that saw the temple as a living part of the landscape, designed to endure its every mood. But a flexible foundation is only the beginning. Once the Earth's tremors are managed, another challenge arises, one of connection. How do you bind these massive stones together so the entire structure moves as one unified, unbreakable whole? This brings us to the second secret, the very skin and bones of the temple's immortality. Masterful stone joinery without a single drop of mortar. Look at the iconic walls of Angkor Wat or the enduring columns of the Greek Pantheon. That breathtaking precision is far more than an artistic choice. It is a deliberate, calculated feat of structural engineering. These stones were not simply stacked. They were meticulously carved to interlock like a perfect three-dimensional puzzle. This technique, known to historians as ashlar masonry, is where the ancient builders' philosophy of permanence became physical reality. Each block was individually shaped so that its weight and the weight of everything above it would be transferred evenly across the entire wall or column. There were no weak points, no spots where stress could gather and begin to crack the stone, but the genius goes even deeper than a flat, tight fit. Often, the masons would carve the mating surfaces of the stones with a subtle, almost imperceptible convexity. Think of it as the gentlest of curves. When these blocks were first placed, they might have touched only along a narrow ridge. Then, as the colossal weight of the structure settled over months and years, something remarkable happened. That immense, steady pressure would cause the stones to compress ever so slightly, pressing those curved surfaces together until they fused into a single, seamless unit. The joints became so exact that, as the old stories go, not even the blade of a knife could be inserted between them. This method solved multiple problems at once. It prevented concentrated stress that could shatter stone. It allowed for the microscopic movement needed during thermal expansion and contraction as the seasons changed, the entire structure breathing as one solid mass. And most critically, it eliminated the greatest weakness of mortar. Mortar, a mixture of lime or clay, is inherently less durable than the stone it binds. It erodes with water, crumbles with frost, and eventually turns to powder. By rejecting mortar, these builders removed the ticking clock from their equation. They created connections that were as permanent as the stone itself. The temple became a monolithic entity, its strength derived from the perfect harmony of its countless individual parts. Yet this raises a profound and practical question. How did they achieve such impossible precision, working with stones that often weighed many tons, using only bronze and stone tools? The answer lies not in a single tool, but in a relentless, generational process of measurement and refinement. The answer lies in a third, breathtakingly simple secret of ancient engineering, the Corbeled Arch. Before the elegant Roman arch with its central keystone was widely known, builders across the globe faced the same monumental challenge. How do you create a roof or span a doorway with nothing but heavy, rectangular stone blocks? Their solution was one of brilliant, incremental daring. They would lay a stone slab across an opening, then place the next slab slightly inward from the edge of the first. Layer by layer, they would repeat this, each new stone cantilevering out a little further over the empty space below, until the two sides finally met at the top. The result was not a smooth curve, but a distinctive triangular or beehive-shaped vault, a testament to patient, stacked ambition. This technique, called corbelling, seems almost childlike in its logic. Yet, it created some of the most enduring interior spaces in history. The Maya used it for the roofs of their sacred temples and observatories. In Scotland, ancient communities built entire underground homes with corbelled stone ceilings. And in Greece, the magnificent treasury of Atreus, a tomb built over 3,000 years ago, showcases its power on a staggering scale. Its corbelled dome soars inward, creating a vast, hushed chamber that has remained intact for millennia. But this method came with a formidable engineering problem. Each of those inward-leaning stones creates a powerful outward thrust, a constant sideways push against the walls that contain it. The ancient builders understood this force intimately. Their countermeasure was both straightforward and massively effective. They built walls of incredible thickness. The walls supporting a corbelled vault weren't just barriers. They were colossal counterweights, massive banks of stone whose sheer bulk and weight pinned everything in place. The outward push of the vault was met and absorbed by the immense inward resistance of the walls. The entire structure became a single, balanced system of opposing forces, locked in a permanent, stable embrace. This approach distributed the weight of the roof down along the entire circumference of the wall, eliminating the need for wide-spanning interior supports. It created spaces that felt both monumental and intimate, chambers where the architecture itself seemed to lean in and listen. While it limited the width of the spaces they could create compared to a true arch, the corbelled vault offered something perhaps more valuable to these builders: absolute, predictable stability. It was a technology of profound patience, where stability was earned not through complex geometry, but through the accumulated, overwhelming mass of perfectly placed stone. Yet, even the strongest roof and the thickest walls are only as good as the materials they're made from. This leads us to a fourth, often overlooked secret, one that begins not at the construction site, but deep within the earth itself. Water is both the giver of life and the most relentless destroyer of stone. While ancient engineers mastered the dance of earthquakes, they faced a slower, more insidious enemy: the steady, patient work of water. This reveals a fourth, profoundly holistic secret. These temples were not just buildings placed on a landscape. They were designed as complete hydrological systems, engineered from the ground up to manage, channel, and defy the very element that could dissolve their foundations over centuries. The builders understood that for a structure to last 1,000 years, it had to survive 1,000 monsoons, 1,000 winters of frost, and the constant, creeping threat of groundwater. At Mohenjo-Daro, one of the world's earliest major cities, the entire citadel complex was built on a massive, man-made platform of baked brick. But look closer, and you find a hidden network of precision. Intricate drains lined with brick channeled every drop of rainwater away from foundations and walls. These weren't afterthoughts. They were integral to the architectural plan, preventing the pooling and seepage that would have slowly eroded the city's base from within. This same foresight appears halfway across the world. The stepped pyramids of Mesoamerica, built in regions of torrential seasonal rain, are crowned with temples that feature elaborate stone gargoyles and sculpted spouts. These are not merely decoration. They are the exit points for sophisticated internal drainage channels that run down through the pyramid's core, directing cascades of water away from the sacred structure's face during a storm. The builders were thinking like geologists, creating artificial watersheds for their stone mountains, but managing surface water was only half the battle. The silent, capillary rise of moisture from the ground posed a constant threat. To counter this, they invented an early form of damp proofing. At the base of walls, just above the foundation, builders would often insert a continuous layer of an impermeable material. In some Greek temples, this was a thin sheet of lead. In others, it was a compacted layer of dense clay or even a course of specially selected non-porous stones. This simple barrier, a damp-proof course, acted as a break. It stopped groundwater from wicking upward into the walls where it could freeze and expand in winter, slowly spalling the stone apart from the inside out. Perhaps the most dramatic marriage of architecture and hydrology is found in the rose-red city of Petra. Here, temples and tombs were not built, but carved directly into the faces of sheer sandstone cliffs. The Nabatean engineers faced a catastrophic danger, seasonal flash floods roaring through the narrow canyons. Their response was nothing short of genius. They carved intricate networks of channels, dams, and cisterns into the cliff faces themselves. These systems captured torrents of floodwater, diverting the destructive force away from the carved facades and instead channeling it into vast underground reservoirs for storage. The temple was not separate from the water management system. The water management system was carved into the very body of the temple. This holistic view transformed water from a threat into a managed resource, and in doing so, they protected their work for millennia. It was a complete philosophy of endurance, considering every possible source of decay. Yet, even with perfect foundations, seamless joints, balanced arches, and managed water, one final, profound question remains. How did these projects, requiring such staggering precision and effort, actually get built? What was the human engine, the social and practical machinery, that could turn this visionary engineering into enduring stone? That final question reveals the fifth and perhaps most elegant secret of all, a principle that wove the spiritual and the scientific into a single, unbreakable thread. We see it in the perfect solar alignment of the great temple at Karnak, or the way the rising sun pierces the heart of Stonehenge on the solstice. This celestial choreography is far more than symbolic ritual. It is a masterclass in foundational engineering. To align a massive stone temple with the distant stars or the precise point of a sunrise requires a geometric perfection that begins not in the heavens, but in the dirt at your feet. Before a single foundation stone was laid, the master builders would engage in a meticulous ceremony of measurement. Using simple, profound tools like the gnomon, a vertical pole that casts a shadow, and long, taut cords, they would map out the temple's entire plan on the ground. They were not just drawing lines, they were etching the paths of celestial bodies onto the earth itself. This process demanded an obsessive attention to leveling and squareness from the very first moment. If your north-south axis is off by even a single degree, the sun will not strike the inner sanctuary on the appointed day. There was no room for error. This relentless pursuit of astronomical accuracy created an unintended yet brilliant structural benefit. It forced the builders to establish a foundation grid of perfect geometric integrity. Every corner was a true right angle. Every line was straight and level across what might be an uneven landscape. This meant that when the immense weight of the stone walls and columns was finally placed upon it, that weight was distributed with absolute mathematical equality. There was no weak corner, no side that bore more load than another. This prevented a silent killer of ancient structures, differential settlement. Over centuries, if one part of a foundation sinks even slightly more than another, immense cracks begin to race up walls, columns tilt, and roofs collapse. The astronomical alignment ritual acted as the ultimate quality control. By ensuring the base was perfectly balanced before they began to build upward, they guaranteed the temple would settle evenly into the earth as a single, unified mass. The structure became as stable as the cosmic order it mirrored. Furthermore, this precise orientation often served a deeply practical, earthly purpose. A temple aligned to the path of the sun could be designed to capture warming rays in winter while providing cooling shade in summer, passively regulating the interior climate. Aligning with cardinal directions could also position the structure to work with prevailing winds for natural ventilation, channeling breezes through colonnades to sweep away dampness and stagnation. So the alignment was never just about faith or just about physics. It was the perfect fusion of both. The spiritual imperative for celestial harmony produced a level of foundational precision that pure utility might never have demanded. The desire to reach for the stars, quite literally, is what gave these temples their rock-solid footing on Earth. It ensured they would not just stand, but stand true for 1,000 years. Yet, with the foundation laid, the walls raised, and the roof secured, one final, haunting mystery lingers in the silent spaces of these ancient halls. But the most astonishing secret of endurance may be hiding in plain sight. Within the very fabric of the walls, modern materials science has uncovered something remarkable about some ancient binders. They were not just inert glue holding stones together. In a very real sense, they were alive. They could heal themselves. Take the legendary Roman concrete that formed the domes of their temples and the piers of their harbors. While our modern concrete is based on Portland cement, the Romans used a different recipe. They mixed lime with a special volcanic ash called pozzolana, often adding in crushed brick or pottery. For centuries, we marveled at how these structures resisted the pounding of seawater. The answer lies in a beautiful chemical accident. When tiny, hairline cracks inevitably form in this ancient concrete, seawater seeps in. Instead of widening the crack and rusting any steel reinforcement, which of course the Romans did not use, this intrusion triggers a hidden potential. The water reacts with the leftover lime and the volcanic ash in the mixture. This reaction grows new, interlocking crystals that slowly fill the crack from the inside out. The material literally patches its own wounds. It is a slow, ongoing process of regeneration that can continue for centuries, making the concrete grow stronger with age in a marine environment. This principle of self-healing was not confined to Rome. In the temples of ancient India, master plasterers often mixed their lime plasters with organic additives. Recipes might include extracts from plants, fruit pulp, or even dairy products like curd. While the full chemistry is complex, these organic compounds appear to have given the plaster a slight flexibility, a resilience against micro cracks. More importantly, they may have encouraged a process of continuous recrystallization over time, where the lime binder would slowly re-knit itself, maintaining a seamless, protective skin over the stonework beneath. The builders may not have understood the molecular science, but through generations of trial and observation, they identified materials that behaved in this dynamic, almost biological way. They were practicing an early form of biomimicry, creating materials that mirrored the regenerative qualities found in nature. This stands in stark contrast to much of our modern Portland cement concrete, which is incredibly strong but also brittle. When it cracks, those cracks tend to grow, letting in water and salts that accelerate decay. The ancient approach was different. It embraced a philosophy of resilience over mere rigidity. They designed materials with a built-in capacity for repair, an allowance for the small failures that time inevitably brings. This secret is perhaps the most profound of all, because it shows us that for these builders, endurance was not a static condition achieved on the day of completion. It was an active process, a dialogue between the structure and the elements, written in the silent, chemical language of stone and lime. It suggests they saw their temples not as finished objects, but as living entities designed to adapt and endure. And this leads us to a final, unifying realization about the true source of these temples' immortality. This dialogue between structure and environment began long before the first stone was ever cut. The seventh secret of ancient engineering is perhaps the most holistic of all. It is the art of strategic site selection, a practice often described as geomancy or reading the landscape. For these master builders, the location of a temple was never an afterthought or a matter of simple convenience. It was a sacred conversation with the earth itself. a search for a place where the physical and spiritual foundations were equally solid. They would send scouts and priests to walk the land for months, observing not just the lay of the land but the feel of it. They sought out stable bedrock, the unshakable bones of the earth, deliberately avoiding floodplains with their shifting silt or hillsides prone to landslides. This single, critical decision eliminated the risk of subsidence, the slow, silent sinking that can doom even the most perfectly built structure over centuries. But their reading went far deeper than simple geology. They listened to the wind, noting how it channeled through valleys, and they would position their temples to use a natural hillside or a dense stand of ancient trees as a permanent windbreak, shielding delicate carvings from erosive weather. They charted the path of the sun across the seasons, choosing orientations that would bathe inner sanctuaries in light on sacred days while using deep eaves to provide cooling shade. They even tested the acoustics of a place. The builders of the oracle at Delphi in Greece, for instance, chose a site where natural springs emitted vapors, but also where the mountain slopes themselves acted as a vast natural amphitheater, amplifying the priestess's whispers into pronouncements that felt divinely projected. This profound symbiosis with the environment turned the entire landscape into a foundational component of the temple's durability. We see it clearly in the theaters and temples of ancient Greece, often built directly into the slope of a hill. The hillside wasn't just a scenic backdrop. It served as a colossal, immovable back wall and as tiered seating, providing inherent structural support and perfect acoustics at no cost of material or labor. The temple didn't fight the mountain, it became part of the mountain. This practice, wrapped in ritual and reverence, was fundamentally sound environmental engineering. It meant the builders worked with the natural forces of the site, rather than exhausting themselves in a constant battle against them. They leveraged the Earth's own strengths to bear the load, used its contours for protection, and harnessed its rhythms for light and sound. In doing so, they didn't just build a temple on the land. They wove the temple into the very fabric of the land, making its endurance a shared responsibility between human craftsmanship and the eternal resilience of the natural world. The final secret of their genius is hidden in plain sight, in a subtle curve that defies the eye. Look closely at the towering columns of the Parthenon in Athens. They are not perfectly straight. From a distance they appear to be, but up close you can see a gentle, swelling curve along their length. This is no accident of time or a flaw in the stone. It is a deliberate, masterful feature known as entoses, a Greek word meaning tension or stretching. This tiny, almost imperceptible bulge represents a breathtaking synthesis of art, human psychology, and deep engineering insight. The ancient builders understood something profound about how we see the world. They knew that our eyes can play tricks on us, especially when viewing massive structures against the bright sky. A column carved with perfectly parallel, straight sides can create an optical illusion. Under the crushing weight of the heavy stone entablature above, those straight lines can appear to pinch inward to concave, giving the unsettling impression that the column is buckling, that it is weak under the load. This visual dissonance would undermine the very feeling of power and permanence the temple was meant to embody. So they introduced a correction. By giving the column that subtle outward curve, they preemptively countered the illusion. The eye, expecting to see a concavity, instead perceives a straight, robust line. The column looks proudly upright, solid, and effortlessly strong. It achieves a state of visual harmony that feels eternally stable. But the brilliance of entoses goes far deeper than visual correction. This slight curve also serves a vital mechanical purpose. Think of a perfectly straight column as a simple, uniform post. When weight presses down from above, the stress travels in a direct, concentrated path straight down the center. The entoses curve changes that geometry entirely. It creates a more complex and more intelligent load path. The weight from the top is now distributed outwards along the gentle arc of the curve, spreading the compressive forces more evenly across the entire width of the column's shaft before they transfer down into the base and the foundation. This prevents stress from concentrating at any single point, which over centuries could lead to microfractures and eventual failure. It is a way of making the stone work smarter, not just harder. This principle of optical refinement was applied everywhere. The stylobate, the platform on which the columns stand, is not flat. It curves upward ever so slightly in the center. The columns themselves are not spaced at perfectly equal distances. They are fractionally closer together at the corners. Every single line that appears straight is, in reality, a calculated curve. The entire temple is a monument to controlled distortion, a collection of intentional imperfections engineered to create the perfect visual and structural whole. This reveals the ultimate goal of these ancient masters. They were not just building structures to withstand physical forces. They were crafting experiences to withstand the test of perception. They accounted for the human element, for the way their work would be felt and seen by generations to come. The temple had to be strong in reality, and it had to feel unshakable in the soul. In the gentle swell of a marble column, we find the complete philosophy of ancient engineering, a seamless, indivisible bond between truth and beauty, between the laws of physics and the poetry of human vision. The quiet swell of a column is a masterpiece of perception, but the sheer scale of these projects defies belief. How could ancient societies without modern machinery possibly manage to quarry, move, and assemble millions of stones, each one weighing as much as a small elephant? The answer lies in a principle so familiar to us today that we might overlook its ancient brilliance: modular construction. These were not one-of-a-kind sculptures carved on site. They were the world's first and largest assembly kits. The ninth secret of ancient engineering is standardization, a systematic approach that transformed impossible dreams into manageable, repeatable tasks. The process began in the quarry, where master masons would establish a set of standard dimensions for the project. Using simple wooden or stone templates, workers would pre-cut blocks, columns, and beams to these exact specifications. An Egyptian pyramid block, a Roman temple column drum, or a Greek wall stone wasn't a unique piece. It was a unit, one of thousands of identical or near-identical siblings. This standardization achieved something profound for structural integrity. When every block in a course of a pyramid is the same height and width, the weight of the entire structure above it is distributed with perfect, predictable uniformity. There are no odd-shaped stones creating points of concentrated pressure. The force flows down through the building in a smooth, even cascade that the engineers could anticipate and design for. This homogeneity is the bedrock of longevity, preventing the random, destructive stresses that come from irregularity. But the benefits were just as much about human organization as they were about physics. Imagine the construction site not as a chaotic scramble, but as a well-orchestrated factory floor. With standardized parts, labor could be divided into specialized teams. One group mastered the art of cutting the standard block, another excelled at transporting it, a third became experts in placing and fitting. This division of labor created efficiency and, crucially, allowed for rigorous quality control. Each block could be checked against the template before it ever left the quarry, ensuring that flaws were caught early, and this system built in a simple yet powerful form of resilience. If a stone was damaged during transport or placement, it wasn't a catastrophe. A replacement could be drawn from the ongoing production of identical units and swapped in without compromising the fit or the strength of the whole. The structure remained coherent, a unified entity built from interchangeable parts. This modular thinking reveals a mindset that saw grand vision and meticulous process as two sides of the same coin. It was the practical engine that powered the spiritual ambition, turning a temple from a singular miracle into a repeatable and therefore achievable feat of engineering. The pyramid rose not as a mysterious monolith, but as the relentless, disciplined stacking of one perfect block upon another, millions of times over. Yet this modular precision points toward an even deeper layer of design, one where mathematics and meaning become one. The 10th secret is the role of symbolic geometry in load distribution. To the ancient master builder, a circle was not just a shape, it was a symbol of the divine, of unity, of cosmic perfection. A triangle was not merely 3 lines. It represented stability, the sacred trinity, or the connection between earth, humanity, and the heavens. This symbolic language was not merely decorative. It was the functional blueprint for the entire structure, proportions revered for their spiritual harmony, like the golden ratio or Pythagorean triangles, were the very rulers used to determine the dimensions of rooms, the spacing of columns, and the curves of arches. These ratios did more than please the eye. They often correspond to naturally stable geometric forms found in nature, shapes that inherently channel physical forces with elegant efficiency. Consider the dome. The specific ratio of its height to its width is not an artistic whim. It is a critical engineering decision that determines whether the stones in the dome are held in a state of pure compression, pressed firmly together, or whether they are forced into tension, being pulled apart. Stone, like all masonry, is incredibly strong when squeezed but weak when stretched. By designing with sacred geometric proportions, these engineers intuitively created forms that kept the vast majority of the masonry in a continuous state of compression. The weight of the dome pushes inward and downward, and the geometry of the shape redirects that force along curving lines of thrust, channeling it safely down into the supporting walls and piers. The perfect circle of the Roman Pantheon's dome is a sublime example. Its proportions create a hemisphere where every stone is essentially leaning on its neighbor, all of them working together to hold the void in the center aloft. The geometry became a mathematical language for describing and ensuring structural integrity. It was a way of embedding stability into the very soul of the temple. When a builder laid out a floor plan based on a sacred mandala or raised a column calculated with the golden ratio, they were doing 2 things simultaneously. They were invoking a cosmic order, and they were solving a complex engineering equation. The spiritual intent guaranteed a level of geometric rigor that pure pragmatism might have overlooked. In this fusion, the temple's form was its function, its beauty was its strength. The silent language of circles, squares, and triangles spoken by the architects was a direct conversation with the laws of physics, ensuring that a structure built for the gods would stand as firmly as the principles that govern the universe itself. The final geometry of a temple is a testament to flawless planning, but its raw material began as a mountain. The journey from quarry to foundation is an enigma of its own, a puzzle of moving mountains one block at a time. How did ancient societies transport stones that weighed as much as 50 modern cars across miles of desert, up steep inclines, or even across the open sea? The solutions they engineered were as diverse as the cultures themselves, yet they all shared one critical goal: to deliver the stone to the site not just intact, but in a state of perfect, stress-free readiness. A single internal fracture, invisible to the eye, could become a fatal weakness under the weight of the finished structure centuries later. This phase was not mere logistics. It was the first and most vital test of the stone's endurance. In Egypt, the method was one of fluid grace. Workers would haul colossal granite blocks on massive wooden sledges. But they didn't just drag them across the burning sand. They built specially prepared causeways and poured water ahead of the sledge runners. The water would seep into the sand, creating a slick, firm mud that drastically reduced friction. The sledge would glide, distributing the immense weight evenly across its broad base and preventing the concentrated point loads that could crack the stone from within. This was moving a mountain by making the earth itself temporarily liquid. the Romans approached the challenge with mechanical ingenuity. They developed sophisticated cranes powered by human treadwheels, a system of ropes and wooden gears. These machines, called polyspastons, used the principle of compound pulleys to create immense mechanical advantage. A small team walking inside a giant hamster wheel could hoist multi-ton marble column drums with controlled, steady force. The key was the slow, even lift. A sudden jerk from a rope or lever could shock the stone, creating microfractures. The crane allowed for a smooth, vertical ascent that kept the stone's internal structure perfectly compressed, just as it would be in the final building. Perhaps the most haunting transport mystery comes from the remote Pacific. On Easter Island, the massive stone moai statues, some weighing over 80 tons, were somehow transported miles from the quarry to their coastal platforms. While theories abound, one compelling idea suggests the statues were not dragged but made to walk. Using a system of ropes, teams could have rocked the statue from side to side, pivoting it on its curved base with each pull. This rocking gait would have distributed the stress dynamically, allowing the giant figure to inch forward without the grinding friction that would have scarred and weakened its surface. Each of these methods, from watery causeways to walking giants, reveals a profound understanding of the stone itself. Before any movement began, the quarry masters had to read the rock like a book. They studied its grain, its natural cleavage lines, and its compressive strength. Granite, for instance, is incredibly strong but can be brittle along certain planes. They would use that knowledge to extract it carefully, sometimes by driving wooden wedges into natural fissures and soaking them with water so the expanding wood would gently crack the block free along a clean line. This careful reading dictated everything. It told them where to position the lifting points, how to orient the block on its journey to keep the grain aligned with future loads, and what kind of motion it could safely withstand. A stone destined to be a column was handled differently than one destined for a lintel, because the forces they would bear in the finished temple were already guiding their journey from the very start. This meticulous, almost reverent handling from the moment of birth in the quarry ensured that only stones of unbroken integrity ever reached the sacred site. It was a quality control process that spanned months and miles, all to preserve the monolithic strength that would define the temple for millennia. The stone arrived not as a battered commodity, but as a consecrated component, ready for its eternal place in the puzzle. Even the simplest architectural forms conceal profound engineering wisdom. While the soaring arch often steals the spotlight, the humble post and lintel system, a simple horizontal beam resting on two upright supports, holds secrets of its own. This is the elemental geometry of Stonehenge's massive trilithons and the elegant colonnades of the Parthenon. At first glance, it seems straightforward. A heavy stone lintel sits directly atop a stone column. But this point of contact is a zone of immense, concentrated stress, a place where the entire weight of the beam and everything above it presses down on a tiny area. Left unmanaged, this pressure would cause the stone at the top of the column to chip, flake, and eventually fail in a process called spalling. The ancient builders solved this with a subtle, brilliant intervention at the junction itself. They understood that stone, for all its strength, is not a perfectly rigid material. It expands and contracts with temperature changes, and the entire structure settles minutely over decades. To accommodate these microscopic movements without causing catastrophic cracking, they engineered a controlled point of contact, often the top of the column, especially the broad, flat stone called the abacus on a classical capital, was slightly hollowed out in the center. Conversely, the underside of the lintel might be given a gentle, corresponding convexity. They did not aim for a full, flat surface meeting another. Instead, they created a small, precise bearing point. Sometimes they went further, carving matching holes into both stones and inserting a bronze or wooden dowel, then pouring molten lead around it to lock it in place. This metal insert acted as a primitive but highly effective bearing. The lead, being slightly malleable, could absorb tiny shifts and vibrations. The bronze dowel provided alignment, ensuring the lintel could not slide off its perch during an earthquake, yet the whole assembly allowed for that crucial fraction of movement. This tiny engineered joint performed multiple miracles. It reduced friction between the two massive stones, allowing them to shift almost imperceptibly without grinding against each other. It transformed a sharp, destructive point load into a distributed load spread over a slightly larger area of the column's top. And by creating a designated, sacrificial point for movement, it protected the main bodies of the lintel and column from developing stress fractures. The junction became a shock absorber, a deliberate, flexible hinge in an otherwise rigid system. This attention to the microscale reveals a mindset that saw the whole structure as a dynamic assembly, even in its most static-seeming form. They were not just stacking stones, they were orchestrating a silent, eternal negotiation between weight and support, ensuring that the meeting point of post and lintel, the very handshake of the structure, would remain firm yet forgiving for 1,000 years. The silent battle against the elements was fought with geometry and shadow. Ancient engineers understood that the most dangerous force their temples faced was not a sudden, violent earthquake, but the patient, unending caress of wind and rain. Over centuries, a steady drip could carve a canyon into granite, and a prevailing wind could sandblast a face from a statue. Their response was a masterclass in defensive design, a layered strategy that turned the temple's own form into a shield. They sculpted the very surfaces of their buildings to shed water and deflect weather with an elegance that feels almost organic. Look at the profile of a classic Greek temple cornice, that horizontal molding at the top of the wall. It doesn't end flush, it projects outward with a pronounced downward sloping edge called a drip edge or a cyma. This isn't just decoration, it's a hydrological command. When rain runs down the roof or wall, it reaches this edge and is forced to let go, dropping clear of the delicate frieze and column capitals below. The water is thrown away from the building's face, preventing it from streaming down and eroding the sculpted surfaces. This same intelligent shaping is visible in the gentle inward slope of the Egyptian pyramids' casing stones. Each massive block was angled slightly back, creating a surface that encouraged rainwater to run inward and down, rather than cascading over the edges where it could pool and seep into the core. The pyramid was designed to dry itself. This philosophy extended to the stone carvings themselves. Master sculptors would often undercut their reliefs, carving the figures so that they projected from a deeply recessed background. This technique, seen in the magnificent panels of Angkor Wat or the metopes of the Pantheon, served a brilliant dual purpose. It created dramatic plays of light and shadow, making the figures appear to emerge from the stone. But that deep shadow was also a permanent umbrella. By recessing the detailed artwork, the sculptors placed it in a sheltered zone, protected from the direct impact of rainfall and from the worst of the sun's bleaching rays. The most vulnerable, finely detailed surfaces were given their own architectural canopy, a permanent recess that kept the weather at bay. The temple's artistic narrative was literally safeguarded by its own geometry. But stone alone could not win every battle, especially in humid, tropical climates where relentless moisture was the enemy. Here, builders employed a renewable armor, lime plaster. Temples across Southeast Asia and Mesoamerica were often coated in a smooth, bright layer of this material. The plaster acted as a sacrificial skin. It was porous enough to allow the masonry beneath to breathe, preventing trapped moisture, but it took the full brunt of the weather's assault. When this outer layer eventually eroded after years of monsoon rains, it was a simple, planned maintenance task to mix a new batch and reapply it. The softer, more easily carved stone beneath, ideal for intricate construction, remained perpetually protected. This was a maintenance cycle built into the very concept of the temple, acknowledging that some defenses needed renewal while the core structure remained eternal. Perhaps the most strategic decision of all happened at the quarry before a single stone was set. Builders practiced a form of material triage. They selected the hardest, most dense, and most weather-resistant stone for the external layers, the corners, and the bases, the places that would face the full force of driving rain, scouring sand, and physical contact. A granite or basalt might form the tough outer shell. Meanwhile, a softer, more workable limestone or sandstone, perfect for detailed interior carvings or vaults, could be safely used within the sheltered heart of the temple. They matched the material's inherent strength to the specific stresses it would endure. This wasn't just using what was available. It was a sophisticated understanding of material science, ensuring that every stone served in the role it was best suited for in the millennia-long campaign against decay. This layered defense from the macro scale of a pyramid's sloped down to the micro choice of which stone went where reveals a profound humility. These builders accepted that they could not stop time. But they could design their temples to negotiate with it, to channel its forces away, and to ensure that what remained told their story for ages to come. Yet even the most perfectly shaped stones required a hidden embrace to become one. Deep within the joints of the Pantheon or the grand Hindu temples of South India, a secret reinforcement lies concealed. Ancient engineers employed iron or bronze clamps, shaped like double-ended hooks or simple bars, to bind massive stones together. The installation was a spectacle of fire and precision. Masons would carve matching channels into the tops of two adjacent blocks, then position a metal clamp within the groove. They would then pour molten bronze or iron directly over it, filling the cavity completely. As the glowing metal cooled, it contracted, shrinking ever so slightly. This shrinkage created a powerful, continuous pull, drawing the two stones tightly together in a permanent, vise-like grip. This technique provided something stone alone could not: active tensile strength. In a world built on compression, where every element was designed to be squeezed, these metal clamps introduced a binding force. They actively resisted the tendency of stones to shift or pull apart under lateral stresses, such as high winds or the twisting motions of an earthquake. The entire assembly was transformed from a stack of parts into a single, rigid mass. But metal presented its own peril. The engineers discovered a cruel irony through earlier, failed experiments. When an iron clamp rusted, the corrosion created iron oxide, a substance that occupies more volume than the original metal. This expansion inside the confined stone channel acted like a slow-motion explosion, generating immense pressure from within until the granite or marble itself fractured. A tool meant to ensure unity could become an agent of destruction. Their elegant solution was a stroke of material genius. They began sheathing the iron clamps in lead. Lead is highly resistant to corrosion, forming a stable protective layer. By encasing the iron in this pliable, waterproof jacket, they created a perfect barrier, isolating the reactive metal from moisture and air. The lead sheath became a timeless prison, preventing the rust that would doom the stone. This hybrid system showcases their sophisticated understanding of different material properties. They used stone for its eternal compressive strength, metal for its flexible, binding tension, and lead for its protective, sacrificial durability. It was a layered approach to resilience, where each material performed a specific, vital role in the silent, eternal collaboration that held the temple together. The silent stones of a temple can sometimes speak in whispers. Beyond their visual majesty, many ancient structures were designed as instruments of sound, a fact that quietly reinforced their physical endurance. In places like the Gol Gumbaz Mausoleum in India, a whisper against one wall travels clearly to someone standing over 150 feet away on the opposite side. This famous whispering gallery is not an accident of architecture. It is the product of a vast, perfectly spherical dome, a shape that creates a continuous sound path along its inner curvature. To achieve this acoustic marvel, the builders had to construct a dome of astonishing geometric purity. Any irregularity, any bump or flat spot, would break the sound path and scatter the whisper. This demand for acoustic perfection forced an unintended yet profound structural benefit. The interior surface had to be flawlessly smooth and continuous. This meant the masonry had to be laid with extraordinary care, creating a shell that was not only acoustically reflective, but also exceptionally monolithic and strong. The very act of chasing a sonic ideal produced a dome with fewer weak points, a more uniform distribution of stress, and a greater inherent resistance to cracking. We see a similar principle in the open-air theaters of ancient Greece. The semi-circular arrangement of stone seats and the carefully calculated slope of the auditorium were designed to project an actor's voice to thousands of listeners without amplification. To prevent disruptive echoes, the surfaces had to be precisely shaped and textured. Rough, irregular stone would create a chaotic flutter of sound, destroying clarity. Therefore, builders meticulously finished the stone, creating smooth, sweeping curves that channeled sound waves predictably. This pursuit of acoustic clarity resulted in auditorium shells of remarkable solidity and cohesion, their forms inherently stable because instability would have meant acoustic failure. This intersection of sound and stone hints at an even deeper layer of ancient intuition, the management of structural resonance. Resonance is the dangerous phenomenon where a structure begins to vibrate violently when exposed to a specific frequency of energy, much like a wine glass shattering when a singer hits the exact right note. An earthquake produces a devastating spectrum of such vibrational frequencies. While ancient engineers may not have had the mathematics to describe resonance, their acoustic work suggests they understood its effects. By designing chambers that dampened or diffused certain sound frequencies by avoiding parallel walls that could create standing waves, or by incorporating specific curves that broke up sound, they were also, perhaps unknowingly, sculpting forms that were less likely to lock into and amplify the destructive resonant frequencies of seismic activity. A space engineered to control sound was, by its very geometry, a space less prone to catastrophic sympathetic vibration. The temple that was built to carry a chant or a prayer to the heavens may have, in that same act, been fortified against the tremors of the earth. This reveals a beautiful synchronicity in their approach, a problem solved for one sacred purpose. Perfect acoustics for ritual or drama delivered a parallel, life-saving solution for structural survival. The legacy of their work is not just in what we see, but in what we might have heard and in the silent, enduring strength that such listening demanded. But for every temple that stands, a dozen others lie in ruins. The perfection we see today was not born from flawless first attempts, but from a long, hard conversation with failure. Ancient builders were relentless students of collapse. When a tower toppled or a vault split open, they did not see just a disaster. They saw a profound lesson, a diagram of stress written in broken stone. The very shape of medieval cathedrals, with their elegant flying buttresses, is a direct response to this kind of forensic observation. Early church builders pushed walls higher and windows wider, only to watch those walls buckle outward under the immense weight of the stone roof. The pattern of the cracks told a clear story. The thrust was pushing out. The solution was the buttress, an external arm of stone that reaches out to shoulder that outward thrust and channel it safely down into the ground. This was not a sudden invention, but an innovation born from repeated, observed collapse. It was an empirical, iterative process of building, watching, and refining, a form of slow-motion research and development that spanned generations. Knowledge of these failures and fixes was not kept in books, but in the living memory of the craft. It passed from master to apprentice in stonecutters' guilds and masons' lodges, through hands-on demonstration and oral tradition. A young apprentice learned not only how to cut a perfect joint, but also why a certain arch shape had failed in a nearby ruin 50 years prior. This created a cumulative engineering tradition, a growing body of wisdom where each generation literally built upon the lessons learned from the collapses of the past. The surviving temple, therefore, is not a solitary miracle. It is the pinnacle of a long, invisible pyramid of tried ideas, discarded methods, and hard-won corrections. Its endurance is a testament to a culture that knew how to listen, even to the loud, catastrophic language of falling stone. These enduring temples speak a shared language, one that was whispered across continents and centuries. The engineering secrets we have traced were rarely born in isolation. They were travelers moving along the slow rivers of trade, carried in the minds of skilled artisans who followed armies or sought new patrons, and sometimes spreading in the wake of conquest itself. This diffusion of knowledge created a hidden global network, a kind of ancient internet where the currency was practical wisdom for defying time. Consider the Corbeled Arch, that brilliant method of stacking stones inward to span a space. We find its distinctive form in the underground homes of Neolithic Scotland, and thousands of miles away, holding up the roofs of Maya temples in the jungles of Mesoamerica. This is not likely evidence of a single inventor, but rather of a convergent solution to a universal problem, discovered independently by human minds facing the same stubborn challenge of gravity. Yet in other cases, the path of transmission is clearer. The revolutionary Roman recipe for self-healing concrete, with its volcanic ash and lime, did not remain a secret of the Italian peninsula. As the empire expanded, so did its building technologies, influencing construction from North Africa to the shores of Britain. The knowledge traveled with legionary engineers and was adapted by local builders who blended it with their own traditions. This cross-cultural exchange was the true catalyst for innovation. A master builder in ancient Cambodia, hearing tales from Persian merchants about ingenious Qanat water systems that tapped underground aqueducts, might have been inspired to adapt the principle for managing the torrential monsoon rains threatening his own temple complex. He would not copy it exactly, but reinterpret it using local materials and responding to specific environmental pressures. This process of hybridization is where techniques were refined and perfected. A solution that worked for marble in a dry, seismic region of Greece might be tested and modified for sandstone in a humid, stable river basin in India. Each adaptation was a live experiment, a trial run across generations that filtered the most resilient ideas. This slow-motion collaboration meant that the universal enemies of monumental architecture, gravity, seismic force, and relentless water, were confronted by a diverse yet interconnected human toolkit. The temple that stands today in one corner of the world may, in its silent stones, hold an echo of a solution first tried in another. Its survival is a testament not just to local genius, but to the patient, worldwide conversation between builders who shared a single, timeless goal: to build something that would outlast them all. The timeline of a temple was often measured not in years but in generations. While we marvel at the finished monument, its construction was a story of patient, ritualistic increments. A king might lay the foundation stone, his grandson would complete the main hall, and his great-grandson's reign would see the addition of an ornate gateway. This glacial pace, dictated by religious calendars, royal successions, and the sheer scale of ambition, was far more than a logistical necessity. It was, perhaps unintentionally, one of the most brilliant engineering strategies ever devised. It created a built-in cycle of rest and testing that modern rapid construction can scarcely replicate. Imagine a foundation laid for a massive central tower. In a modern project, the superstructure might rise within months, piling thousands of tons of weight onto concrete that is still chemically curing and earth that is still compacting. This rush can trap stresses, leading to subtle shifts and long-term instability. The ancient method was different. After that foundation was complete, years or even decades might pass before the next major phase began. During this sacred pause, something critical happened. The ground beneath the foundation had time to fully settle and consolidate under the initial load. The mortar, if used, could undergo its complete, slow chemical cure, reaching its ultimate strength. The entire assembly experienced the full cycle of seasons, expanding in summer heat, contracting in winter cold, being soaked by rains and dried by winds. It was allowed to find its natural equilibrium, to settle into its permanent place in the landscape. Any weakness, any uneven settlement would reveal itself during this long observation period. Cracks would appear, shifts would become evident, and the builders of the next generation could see the problem and adapt their plans. They might reinforce a wall, adjust the design of the next section, or choose a different material. This pause and test cycle turned time itself into a quality control inspector. The temple grew organically, each new phase built upon a base that had already proven itself stable over decades. This incremental approach also distributed the monumental financial and labor burden across generations, making such impossible projects socially sustainable. It wove the temple into the very fabric of the community's life, as its rising form became a constant in the backdrop of changing lives. The ritualistic rhythm of construction, therefore, was not an obstacle to greatness. It was the hidden mechanism that ensured the work would not just be grand, but would endure. The slow, generational dance between stone and earth created a dialogue with time, and from that patient conversation arose a stability that haste could never achieve. A finished temple was never truly finished. Its survival for 1,000 years was not a passive accident of good engineering, but the result of an active, living promise. Beyond the brilliant architects and the legions of stonecutters, a quieter, often neglected force ensured these monuments endured, a deep cultural tradition of perpetual maintenance. Inscriptions carved into temple walls in Egypt, detailed manuals from ancient India, and civic records from Rome all tell the same story. They document endowments, gifts of land, treasure, or tax revenue specifically designated for the structure's eternal care. This was not emergency repair work. It was a scheduled, cyclical ritual as predictable as the seasons. The funds paid for teams to clear silt from drainage channels before the monsoon, to reapply protective lime plaster to sun-baked walls, and to carefully replace the bronze clamps that might have begun to corrode after centuries of service. A temple was not a static museum piece. It was a living institution, often with a dedicated staff whose sole purpose was preservation. Think of them as the original heritage conservationists. Their work was profoundly proactive. They understood a universal truth that any homeowner knows. A small leak ignored today becomes a flooded ruin tomorrow. By continuously monitoring and addressing minor wear, they prevented the cascade of failure. A single blocked drain could lead to water pooling against a foundation, which could soften the earth and cause a wall to tilt. A single cracked lintel, if not stabilized, could transfer fatal stress to the columns below. This maintenance culture transformed the temple from a mere object into a perpetual process. It represented a societal vow, a commitment from the entire community that this sacred anchor in their world would be sustained across the limitless horizon of time. The builders did not just create a monument and walk away. They established the systems and the social will to keep it alive. This ethos, where preservation was a continuous cultural priority woven into the fabric of faith and civic duty, is something modern conservation efforts deeply admire but often struggle to replicate. Today, we marvel at a ruin and fund a restoration project, but the ancient world built something more powerful than a project. They built a tradition, an unbroken chain of care that saw the temple not as a relic of the past, but as a breathing, eternal citizen of the future. Laser light now traces the same joints that ancient hands once fitted by feel. With tools like high-resolution laser scanning and powerful computer simulations, modern engineers are performing a kind of archaeological forensics on these timeless structures. They are not just admiring the craftsmanship, they are quantifying it, translating intuitive genius into hard data. The results are a profound validation. What was once considered mystical or impossibly advanced is now revealed as a sophisticated, empirical science of endurance. Take the famed polygonal walls of the Inca at sites like Sacsayhuaman. To our eyes, the stones fit together in a complex, jagged puzzle. But when engineers scan these surfaces with lasers that map to a fraction of a millimeter, they discover the true secret. The fit is not just tight on the visible face. Each stone is subtly sculpted with a concave depression on its backside that mates perfectly with a convex bulge on the stone behind it. This creates a three-dimensional interlock, a hidden geometry that makes the entire wall behave like a single, flexible mass during an earthquake, rather than a collection of rigid blocks. The builder's intuition for form and force is made visible in a digital point cloud. Computer simulations take this understanding even further. Using a technique called finite element analysis, researchers can create a virtual model of a structure like the Pantheon and subject it to simulated seismic waves. The model reveals how the building's famous refinements, the gentle intosses of its columns, the slight curvature of its platform, work together to dissipate destructive energy. The simulation shows stress flowing in elegant, distributed pathways, avoiding concentration at any single point. It proves mathematically what the builders knew phenomenologically, that controlled flexibility and optical perfection were one and the same engineering principle. This digital testing ground confirms that these were not artistic flourishes, but calculated responses to very real physical threats. Perhaps the most startling rediscovery comes from the laboratory, where chemists have unraveled the molecular recipe of Roman maritime concrete. For centuries, we assumed our modern concrete was superior. The science tells a different story. The Roman mixture of lime, volcanic ash, and seawater encouraged the growth of rare, plate-like crystals that interlace through the material. These crystals act as a reinforcing fiber mesh, preventing cracks from spreading. More astonishingly, the concrete continues to chemically react with seawater for centuries, forming new minerals that fill any microfractures. It is a material designed not just to resist time, but to improve with it. This is not a lost art we cannot replicate. It is a science we failed to recognize, one that modern researchers are now actively trying to emulate for seawalls and tidal energy projects. This modern validation is deeply humbling. It dismantles the old myth that these achievements were the product of alien intervention or lost super science. Instead, it reveals something more powerful, the cumulative power of human observation, patience, and tacit knowledge. These builders were master natural philosophers. They spent generations watching how stone fractured under load, how water pooled and eroded, how structures responded to tremors. They conducted experiments on a monumental scale, learning from collapses and refining their techniques over centuries. Their knowledge was not written in textbooks, but encoded in the muscle memory of guilds and the oral traditions of master masons. They possessed a deep, intuitive feel for the behavior of materials, a sense of how stone wanted to bear weight, how lime wanted to cure, how forces wanted to flow. Today, as we face the urgent need for sustainable and resilient infrastructure in an age of climate change and seismic risk, the circle of knowledge is turning. Engineers are not just studying these ancient secrets out of historical curiosity. They are looking back for inspiration. The principles of seismic isolation, self-healing materials, passive climate control, and holistic site selection offer powerful alternatives to the energy-intensive, often brittle paradigms of 20th century construction. The goal is not to abandon steel and glass, but to integrate this ancient wisdom, this proven, long-term thinking into the cities of tomorrow. In a very real sense, the future of durable, harmonious design may depend on our willingness to listen once more to the silent, enduring lessons of the past. The Pantheon in Rome holds its breath beneath a dome of open sky. For 1,900 years, this vast concrete ceiling has hung suspended without a single piece of internal steel reinforcement, a silent challenge to every engineering assumption we hold dear. Its survival is not a single secret, but a layered symphony of solutions, each one addressing a fundamental law of physics with elegant simplicity. The first genius lies in the dome's very substance. The Romans understood that the greatest threat to such a span was its own weight. Their solution was a material gradient of breathtaking intelligence. As the dome rises from its supporting drum, the concrete itself transforms. At the heavy, load-bearing base, the mix is packed with dense, strong basalt aggregate. But with each successive layer, the recipe changes. The heavy stone is gradually replaced by lighter materials, first a volcanic rock called tufa, and finally, near the top, by porous, feather-light pumice. This is not a random choice, it is a deliberate, calculated lightening of the load. The dome becomes progressively lighter as it ascends, minimizing the cumulative weight and, most crucially, the outward thrust pushing against the walls below. It is architecture thinking like a bird, where every gram saved adds to the possibility of flight. This principle of weight reduction finds its most beautiful expression overhead. Look up into the Pantheon's interior, and you see not a smooth shell, but a grid of sunken, square panels, the coffered ceiling. For centuries, these were admired as pure decoration, a geometric play of light and shadow. But their purpose is profoundly structural. Each coffer is a carefully carved void, removing cubic meters of heavy concrete that would otherwise add tons of unnecessary mass. Think of it as sculpting away everything that isn't essential to the dome's strength. The coffers thin the shell at its center, where stress is lower, while leaving a robust, continuous framework of concrete ribs along the lines of greatest force. This achieves a double victory. It dramatically lightens the dome, and it creates a deeper structural profile without adding actual thickness, increasing stiffness and stability. The beauty is literally carved from necessity. All this weight, even when minimized, creates an immense outward push. The Pantheon's final defense against this thrust is not a flying buttress, but something far more monolithic, its own walls. The drum supporting the dome is not a thin shell. It is a staggering 20 feet thick in places, a continuous ring of brick-faced concrete that acts as a permanent, unshakable buttress. Within these walls, hidden from view, are enormous brick arches embedded in the concrete, channeling loads down through the masonry in organized, efficient pathways. The entire structure is a single, cohesive entity. The thick drum contains the dome's thrust, the graded concrete manages its weight, and the coffers lighten its load. They all work in a perfect, balanced conversation. Yet, for all we understand, the Pantheon guards a final mystery. Modern engineers can analyze its form and guess at its composition, but the exact recipe of that Roman concrete, the precise blend of lime, volcanic ash, and aggregate, and the full mathematical intuition behind its proportions remain partially elusive. We can simulate its behavior, but we cannot perfectly replicate the material or the centuries of tacit knowledge that went into its placement. It stands as a masterclass in an ancient, holistic science of building, where material, form, and force were understood not as separate problems, but as interconnected parts of a single, enduring truth. Its open oculus, that great eye to the heavens, seems to ask not how it was built, but whether we have yet learned all it has to teach. The silent moat surrounding Angkor Wat holds a secret deeper than any treasure. While its mirrored surface creates that breathtaking reflection of the temple spires, its true purpose was to anchor the entire complex to the earth. This vast man-made expanse of water, often interpreted as a symbolic ocean or a line of defense, was in fact a brilliant, large-scale piece of hydrological engineering. The builders of Angkor faced a formidable geological challenge. Their magnificent temple, constructed from millions of sandstone blocks, sat upon a foundation of porous, clay-rich soil. In a climate of extreme seasonal swings, scorching dry periods followed by torrential monsoon rains, this soil was inherently unstable. When it dried out, the clay would shrink and crack, creating voids and pockets of weakness. When saturated, it would become soft and expand, losing its bearing strength. Either scenario threatened to cause the colossal structure above to tilt, settle unevenly, or crack apart. The moat was their elegant, monumental solution. By encircling the temple with a permanent body of water, they created a giant hydraulic regulator. The water in the moat constantly seeped into the surrounding earth, maintaining a consistent level of moisture in the soil throughout the dry season. This prevented the dangerous shrinkage and cracking that would have undermined the foundations. Think of it as giving the earth a perpetual drink, keeping it gently swollen and stable. During the intense monsoon rains, the system worked in reverse. The moat acted as a massive overflow basin, absorbing the deluge and preventing a catastrophic rise in the water table directly beneath the temple. By managing this hydraulic pressure, it stopped the soil from becoming a fluid, unstable slurry that could liquefy under the temple's immense weight. In essence, the moat created a perfectly balanced, consistent soil environment, a stable platform that remained unchanged across seasons and centuries. This simple intervention transformed a volatile foundation into a reliable one. It showcases a profound understanding of soil mechanics and environmental equilibrium, turning a potential weakness into a source of enduring strength. The beauty of the reflection was merely a bonus. The true miracle was the unwavering stability it represented below the surface. Sometimes resilience looks less like perfect symmetry and more like a defiant, graceful lean. In the eastern Indian state of Odisha, the temple of Lord Shiva at Huma does not stand upright. It tilts at a precarious angle, its main tower and surrounding structures all leaning in the same direction, as if caught in a perpetual, slow dance with gravity. For centuries, this apparent flaw has been its greatest strength. While the Leaning Tower of Pisa is a famous case of foundational error, the Huma temple presents a different, more intentional lesson in survival. Its enduring stance reveals a profound engineering secret, that sometimes the key to longevity is not in resisting movement, but in mastering it as a unified whole. The temple's survival hinges on a single, brilliant decision made at the very beginning. Unlike most large structures, which are built on separate foundation stones or footings, this entire temple complex rests upon one colossal, monolithic slab of rock. This was not merely a convenient bedrock outcrop, it was a calculated choice. The builders identified a single, enormous stone plate and constructed everything, the central shrine, the hall, the gateways directly atop this unbroken base. This created a fundamental unity between the building and the earth it sits on. When the soft, alluvial soil of the riverbank began to shift over time, likely due to the slow, persistent flow of the nearby Mahanadi River, the entire slab began to tilt. But because the temple is fused to this single, rigid plate, it tilted with it. Every wall, every column, every carved deity moved in perfect, synchronized harmony. This is the critical distinction. In a conventional building with separate foundations, one corner might sink faster than another. This differential settlement creates shear forces, immense twisting stresses that race up through the masonry, pulling it apart until a fatal crack appears. At Huma, that twisting force was eliminated. There are no independent parts pulling in different directions. The entire temple behaves as one solid, Chinese letter, Chinese letter, Chinese letter block. It moves as a single entity, so the stresses that would normally tear a structure apart are instead distributed evenly throughout its entire mass. The stones are not fighting each other. They are all leaning together, sharing the burden of the tilt. This principle of monolithic movement is a cornerstone of modern seismic design, where engineers aim to make a building move as one unit during an earthquake, preventing individual components from collapsing. The ancient builders of Huma arrived at this solution not through calculation, but through a holistic understanding of material and site. They accepted the inevitable that the ground would move, and they designed a system that would move with it gracefully and entirely. The temple's lean is not a sign of impending failure, but a testament to a flexible, brilliant strategy for endurance. It stands as a powerful reminder that in the ancient world, engineering wisdom was not always about achieving perfect static stability. Sometimes it was about designing a structure that could find a new, permanent equilibrium, even if that meant standing at an angle to the rest of the world. Decoding these ancient secrets does more than satisfy our curiosity. It lays upon us a profound and urgent responsibility. For the first time in centuries, we can truly understand the language of their endurance, and with that understanding comes a duty to act as guardians, not just spectators. The tragedy would be to use our modern knowledge in ways that undermine the very genius we seek to honor. Consider the well-intentioned but catastrophic mistake of using modern Portland cement to repair ancient stonework. Cement is rigid, impermeable, and chemically incompatible. When it traps moisture against historic stone or prevents the natural, microscopic movement these structures were designed for, it can accelerate decay, causing the original masonry to crack and crumble from within. It is a repair that becomes a new, faster-acting disease. Similarly, the vibration from heavy tourist traffic, the altered water tables from nearby construction, or even the chemical breath of millions of visitors can inflict more damage in a decade than natural weathering did in 1,000 years. The true lesson from the master builders is clear. We must learn to work with these temples on their own terms. This means using compatible, breathable lime mortars that mimic ancient recipes. It means employing minimally invasive techniques, like using lightweight drones for surveys instead of erecting massive scaffolding that stresses fragile walls. It involves listening to the structure, using our scanners and sensors to understand its unique rhythm of settlement and stress before we ever touch a stone. Preservation today is an act of deep humility. It requires us to set aside our assumption that newer means better and instead adopt the ancient builders' patient, observational mindset. We are not here to fix them in a modern sense, but to sustain the delicate equilibrium they have maintained for millennia. Yet this responsibility extends beyond conservation. These temples offer us something even greater, a blueprint for our own future. In an era of climate uncertainty and resource constraints, their principles are strikingly relevant. The ancient art of seismic isolation teaches us to design buildings that dance with tremors, not resist them to the breaking point. Their use of passive cooling, strategic orientation, and self-healing materials points toward a sustainable architecture that works in concert with natural forces, rather than consuming vast energy to fight them. The temples stand as monumental proof that longevity is not about brute force, but about intelligent harmony. They challenge us to build with a vision that looks centuries ahead, not just decades. To do so requires reviving the most human of their secrets, a commitment to stewardship that spans generations. their survival was never an accident. It was the result of a cultural vow, a promise from each generation to the next to be keepers of the flame. Our task now is to make that same vow, to apply both our advanced science and recovered ancient wisdom with a gentle hand and a long view. In protecting their legacy, we may just rediscover how to build a world worthy of lasting. From the seismic isolation of Baalbek to the self-healing concrete of Rome, the ancient world was a crucible of engineering innovation, but it was fueled by something far deeper than mere technique. It was driven by a sacred quest for permanence, a profound need to create something that would whisper to the future. These temples survived not by accident, but by a masterful design that harmonized the spiritual with the utterly empirical. Every choice, from the alignment with a star to the shape of a joint, was a conversation between faith and physics, a way of making cosmic order tangible in stone. They understood that to build for eternity, you could not fight the natural world. You had to listen to it, to learn its rhythms of tremor and tide, and then build in respectful harmony with those forces. Their legacy is a stone library of knowledge, written in the silent language of load paths and water channels. It challenges our modern assumptions about progress, reminding us that our most advanced materials are not always the most resilient, and that speed of construction can come at the cost of longevity. True durability, as they proved, is born from patience, from generations of observation, and from a deep, almost reverent respect for natural laws. As we now face our own monumental challenges of climate change and the urgent need for sustainable construction, we might find that our greatest resource is to look back. The principles encoded in these temples, passive cooling, seismic resilience, self-repairing materials, and holistic site integration, offer not just historical insight, but a viable blueprint for a resilient future. They teach us that endurance is a philosophy before it is a formula. So the next time you stand before an old temple, look closer. See past the grandeur to the quiet genius in the joints, the intelligent slope of a wall, the hidden logic in its stance. What ancient secret will you discover? Share what you find in the comments below. If this journey through the wisdom of stone has sparked your curiosity, subscribe for more explorations into the hidden histories that shape our world.